So we have learned differentiation last year. Just have to think about what we have learned last year. Basically, we learned one rule, which is the derivative of a polynomial, x to the power of n, and then we can differentiate that to become n times x to the power of n minus 1. So drag the power into the front and reduce the power by 1. Also, we have go through all the definitions, but I'm not sure how much you can still remember now. Also, we learn why we need derivatives, because that's the gradient of the tangent at a particular point. So that's, I think, what you know from differentiation, like in year 11. Well, we will relearn everything you have learned in year 11, plus we'll learn some new rules for differentiation. For example, we're going to learn how to differentiate sine, cosine, and tangent functions. We'll learn how to differentiate exponentials, and we'll learn how to derive logs. But other than that, everything else will be the same as what you have learned in year 11. So before we start, I have changed the order a little bit. I put 9L into the front to teach it before we start talk about the rule, the actual rule. Why I put this here? Because it involves some evaluation of limit and can give you better understanding on things. So there are 4 definitions basically in differentiation. They are defined, limit, and the next level will be continuity, and the next level will be differentiability. Okay, so 4 definitions here. For those 4 definitions, well, it's very important to know how to prove them or how to discuss whether it's continuous or not. Last year, SAC, we give a question on continuity. It's a continuous point, and I asked students to explain why it's a continuous point, and it's very badly done. Okay, so they know it's continuous, but they can't say why it's continuous. There's pretty some couple of laws or couple of lines you need to write for talking about all of these definitions. So you need to pay attention in this class. Okay, very important topic. Let's talk about define. Define is the easiest thing in this 4. So a define is nothing to do with differentiation. It is when you have x equals to a, you can give a y value. Then we say at x equals to a, it is defined. So when you sub x equals to a into the function, you got a value. Then we say it is defined. What is not defined then? Open circle is not defined. Okay, so we have that is not defined at this point. Okay, let's say that's 2. And that's 2 as well. So at x equals to 2 is not defined. Because when you sub x equals 2, there's no y values, you can't achieve anything. So it's not defined at that point. But also another thing is not defined will be, well, for example, the graph looks like this. That's x equals to minus 1. So at x equals to minus 1, it is not defined, because positive infinity or negative infinity, we don't say it is defined. Okay, it's not a value. Infinity is not a value. Okay, a value must be a number like 1, 2, or negative 100 or 10,000. Infinity is not a value, so it is not defined here. We can't get the value. Also, asymptotes means you can't get the value at x equals to negative 1. So those 2 graphs are the case which is not defined. Okay, at the point it is not defined. All right, then we talk about limit. Okay, limit is the thing I feel is the most difficult to explain. So what is limit? Limit is when you get as close to a value and what the y value approaching to. So which is doesn't mean when you get step onto that point, what is the y value? It says you're walking towards to a point. What is your value approaching to? Well, you're getting close to which value? So let's use this graph as an example. Okay, I said I want to talk about the limit x approaching to 2 of fx. I want to investigate the value of this function when x approaching to 2. So you need to approaching to 2 from both sides. So my way of looking at this is I will treat this graph as a building. Let's consider that's a big building. Okay, so horizontal is the location, like 1, 2, 3, 4. So I'm approaching location 2. Okay, I'm approaching to location 2. And then the vertical one will be the height. Okay, the height of the building. So basement, level 1, level 2, level 3. And then the graph itself, you can treat as a pathway. Okay, so people can walk on that. Okay, people can walk on that pathway. So now I want to approaching to location 2. So where's location 2? Here's location 2. Okay. Oh, it's not really on the point. Okay, here is the location 2. So people from both sides trying to go towards that level, okay, that wall. So want to head towards that wall. So someone on the left hand side will take this pathway here. Okay, this red pathway here. So someone walk along that level. So actually someone will at a higher level and then approaching, go head towards there's a wall. Think about there's a wall at location 2. You can't really step onto the location 2. You can't really stand there because there's a wall. You can't stand there. But you can get as close as you can to the wall. You can just really go a little bit close, a little bit close. So you're actually on a higher level. But when you walk towards that wall, your level, like how high you are, is about level 2. Okay, let's say a level 3. Let's make this value 3. It's easier to talk about. Your height will be approaching to level 3. You can be 3.01. Okay, and then as you walk a little bit below, there will be 3.005, 3.004. So the value will keep decreasing, but never really get onto 3 because you never can step onto that point. But you're always decreasing the value towards 3. Okay, that's someone walk on the left hand side, what can happen. And someone walk on the right hand side will take that blue path. Okay, so we go, well, you can only walk on that. Walk there. So you actually at the lower level, which is below level 3. But you can increase, and then increase to 2.99, 2.995, 2.999. So you will get very, very, very close to level 3. You are approaching to level 3. As you walk a little bit further, you will get a little bit increase towards 3, but you never really reach 3. That is the definition for limit. Limit is when you walk towards there, what is your y value approaching to? Okay, you never really get onto that. It can be 2.999. On the other side can be 3.0001. But it's never really reached 3. But you can see there's a trend is getting to 3. Okay, it's trying to get to 3. So therefore, we have an open circle there. It doesn't matter. It doesn't matter that's a closed circle or open circle. I don't really care about that point that much because I will never really step onto that point. It's like the point near to that, what you can approaching to. So this question will say limit x approaching to 2 will equals to 3 because people from both sides of the wall will all head towards to the same point. They're all trying to get to the same level. So that level is level 3. They're all trying their best to reach level 3. So the limit is 3. Okay, the limit is 3. But it's not that easy to just say the limit is 3. So what else we need to think about? Well, it's not what else. That's all what we think about. We have a limit. But to make a limit exist, so for a function, a limit exists at x equals to a when the left hand side and right hand side limit exist and are equal. So you want something exist and are equal. So in this question, what we can write is lim x approaching to 2 from negative, which is the left hand side, of fx gives you at level 3. So that point can be 3.001, 3.0001, 3.000001. So it's approaching to 3. It's approaching to 3. And the limit at x approaching to 2 plus fx equals to 3 as well. That's what you need to discuss. If ask you whether it exists or not, you need to discuss that. You need to discuss the left hand side and right hand side. So right hand side, people walk up, okay, walk upstairs, and then you can get 2.9, 2.99, 2.999. So it's approaching to 3 as well. Therefore, you can see the lim of x approaching to 2 negative fx equals to lim x approaching to 2 from positive of fx. Therefore, the conclusion is lim x approaching to 2 fx equals to 3. 4 lines you need to write to talk about limit exists or not. Okay, 4 lines you need to write to talk about limit exists or not. Alright, so the concept of limit as something we are approaching but may not necessarily reach is a limit. We can all head towards but never reach. That's the definition for limit. So it doesn't really matter to that particular point to be an open circle or a closed circle. Whether it's defined or not doesn't really matter, because we don't really want to get to that point. We just want to go approaching to that point. Okay, that's the definition. Let's have a look at the 4 graph below here. We talk about the not differentiation, whether it's defined or limit exists, okay, at x equals to 0. Because when you ask f0, that means whether it's defined or not. So we investigate on x equals to 0 at that point. So let's have a look. Do you think this function is defined at x equals to 0? Defined. Is it defined? When x equals to 0, do you have a y value? Yes or no? Yes. So it is defined. Okay, f0 equals to 2. So defined. Okay, it is defined. Do you think limit exists? Do you think limit exists? 0, okay, level 0, not level, location 0 is this location, okay? So the blue thing, the graph is the path. Do you think if you have a person walk on the left and a person walk on the right, will they head towards the same point? Yes, the limit will exist. So if a person walk on this line, so you will say limit x approaching to 0 from the left of fx equals to 2, because it's approaching to this point here. And then limit x approaching to 0 from the right of fx equals to 2 as well, because someone walked along that path from the right hand side. So limit x approaching to 0 negative of fx equals to the lim x approaching to 0 positive of fx. So limit x approaching to 0 of fx equals to 2. It is exist. It is exist. So for the first graph here, it is defined and it is limit exists for the point x equals to 0. That's the first graph. Let's have a look at the second one. Is it defined at x equals to 0? No. Okay, not defined. It's not defined at x equals to 0. Do you think limit exists for that one? What's the limit value then? What's the limit value? What, like the lim x approaching to 0 fx equals to what? Well, limit x approaching to 0 here equals to 2. So for this graph, what's the limit equals to? Infinity? Infinity is not a value. Infinity is not a value. It's not a number. Well, my question is, if you go from left hand side and you go to right hand side, and then when you're trying to head towards the location 0, are they head towards the same point? Is there a point they all can head towards to? Is there one point? The curve looks like this. Okay, the curve looks like this. When they go up, 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 are they head towards the same point? Where is the same point? Where is that point? There's no point even at 0. There's nowhere they all head towards to. That's two separate graphs. Can you see that's two separate graphs? There's even no place they can try to head towards to. It's keep going forever to the top. There's no value they can head towards to. As I said, infinity is not a value. Infinity is something does not exist. So what we need to say here is limit of x approaching to 0 from the negative side of fx does not exist. Why it does not exist? Because when you go from the left, go up towards to 0, you're trying to approach a really high level, which is infinity. That doesn't exist. Approaching to infinity means doesn't exist because you can't name a number it is actually approaching to. You can't name it, so that does not exist. Okay, so you can say left hand side of fx does not exist. You can also say right hand side does not exist either. So it's enough to make a conclusion already now. So lim x approaching to 0 of fx does not exist. Well, one side does not exist, the other side definitely, well, doesn't matter whether the other side will exist or not. It just can't be limit exist. Because both sides needs to exist and they needs to be equivalent. Then we can say it is limit exists. But one side already doesn't exist, so the other side doesn't really matter. So it is limit not exist. Okay, limit does not exist here. So this question tells us infinity is not a value. Infinity means does not exist. Okay, so it is not defined at x equals to 0, and it is not, a limit does not exist at x equals 0 for this question here. Alright, next one. The third one. Do you think it's defined for the question? Yes? So what's f0? Yeah, -1. And do you think limit exists? Well, if we say no, we need to reason it. Even if we say yes, we still need to reason it. So we always need to mention from the left and to the right. So lim x approaching to 0 from the left hand side of fx. So someone will walk along this path. Okay, well, that's the location 0. Okay, that's the wall. So when I head towards to this wall, I will be approaching to -1. I'll be approaching to -1. When I walk from the right hand side of the function, well, right hand side is here. I'll go head towards to 0. Okay, head towards to 0 because that's the location. I'll head towards to that point. I can't go to the bottom point here. So the conclusion we can make is lim x approaching to 0 from the left is not equivalent to the lim x approaching to 0 from the right. So lim x approaching to 0 of fx does not exist. And that's how we make the discussion. That's how we make the discussion whether limit exists or whether limit does not exist. Okay, let's have a look at the last one. Last one, limit exists or not, defined or not first. No, okay. X equals to 0 is not defined because there's an open circle. Do you think limit exists or not? Limit exists or not? Yes. So we need to say lim from x approaching to 0 from the negative side. Okay, that's the 0 location. Okay, when I walk, you can see I will walk towards to the same point in the end. So lim x approaching to 0 from the negative of fx equals to 1. Lim x approaching to 0 from the positive of fx equals to 1 as well. So lim x approaching to 0 negative will equals to lim x approaching to 0 from the positive. So lim x approaching to 0 of fx equals to 1. Okay, let's have a look at those 4 questions here. For the first one, limit exists and it is defined. For the second one, it is not defined, limit does not exist. For the third one, it is defined but limit does not exist. For the fourth one, limit exists but is not defined. Which is 4 example shows us limit and define are completely 2 things. Okay, there's no connections between each other. It can both define and limit exist, can both does not exist. And can one exist, the other one does not exist. So there's no influence between each other. We need to decide that separately. Okay, we need to decide that separately and better from a graph. Okay, better from a graph. If you go to the next page, well, next page basically talk about nothing. First one is just tell us limit will exist regardless whether the point is defined or does not define. Well, for that one, at x equals to 1, it is limit exists. For that one, but at x equals to 1 is not defined, it still limit exists. Still limit exists because when people walk from the left, I will go towards to that point. When I go from the right, I will go towards that point as well. Head towards the same thing, limit exists for both of that. These are 2 graphs shows you that when limit does not exist, when there's a vertical jump or there's a horizontal jump, then we say limit does not exist. We can see if you all head towards level 0, the limit does not exist because 2 different points. Also from that, that's a horizontal jump. We can see here, well, there's a gap in between. So limit does not exist. Okay, so head towards 2 different points, limit does not exist. Okay, moving on to example, next page, question 3. Okay, page 3. There's 4 theorems, but I want you to only remember the first one. Well, the other 3 is really useless. What the other 3 talk about is when you have 2 functions add together, you find the limit. That will be the same as you find the limit of separate functions and then add them together. Or when you have some 2 functions subtract, you find the limit separately and subtract it. When you times 2 functions, find the limit separately and times it. When you divide 2, find the limit, that will be the same as you find the limit and then divide them. So it's nothing really fun. We don't want to do that. But the first one is important. The first one is that the limit at anywhere of a constant will still be the constant itself. Okay, the limit of anywhere of a constant is still be the constant itself. So which means lim x approaching to a of, for example, 5 is always 5. Doesn't matter what is a. Why is like that? Because think about the function y equals to 5. It's just a horizontal line. Yes? Well, at any point got a height of 5. It doesn't matter which point you're trying to head towards. It's all the same level. It's not going to change. So we have just the limit is just the constant itself. And then we talk about evaluation. How do we evaluate limits? For example, well, what's the answer for the first one? What's the answer for the first one? 10. Yeah, 10. The limit of a constant will just be the constant itself, just 10. But when I involve other like variables x, y, what we need to do? The basic rule we need to follow is, can we substitute that value directly? Can we evaluate that by substitute what values in? When we sub x equals to 0, is it possible to sub x equals to 0 in this function? Is there anything wrong we can't substitute? No? Then we can just substitute that directly into the function to evaluate the limit, if we can. So this one we can. When we sub x equals to 0, we get rid of the lim. So we sub that in, that's 2 times 5, that's just give me a 10. Just sub x equals to 0. Okay, we sub x equals to 0, we have that value 10. Okay, for C, can I substitute the value directly? Is there anything wrong I can't substitute? No. Okay, I can substitute and evaluate. Then we will substitute that directly. 5 minus 7 times negative 2 and negative 2 minus 4. That gives me negative 19 over 4. So that's the limit of that function. When I can substitute that. Okay, when I can substitute that. Let's have a look at D. Can I substitute that? Why I can't? Everyone, we need to think. Wake up. Not because of the square. Why I can't substitute negative 3? Okay, good. One wake up already. I can't substitute because the denominator will be 0. Okay, can't substitute because denominator is 0. So when we can't substitute, we need to do something to make it available, like I can substitute. So when I do something to the function, I need to keep the lim approaching to negative 3 there. Because I haven't substituted yet, that won't disappear. What I can do, I can divide x plus 3 from top and bottom. Okay, that's what I will get. Can I substitute it now? Yes? Yes. Then I will substitute that. That's just 0. We'll sub negative 3, that's just a 0. Now I can substitute, I will substitute that. Okay, my question is, well, 2 questions. First of all, what type of function is that? What's that? What function is that? Don't tell me you can't see what function is that. Linear, everyone, linear, wake up. 2 over 5x plus 3 over 5. Is that a linear? 6 over 5. Is that a linear? Before we do anything, can you see that's a linear? Well, kind of a linear, but do you think they are exactly equivalent? Can I say this is that? Can I say that? Why? What's wrong? 0? 0? Kind of, not really very accurate. What is the implied domain for the top function? What is it? R except -3. It is the linear. It is the linear. But you need to think about the implied domain. The implied domain will be considered at the very beginning, not after you simplify it, not after like you do all this kind of things to it. You need to talk about the implied domain. This is the question. We have some restrictions on this question, which is R except -3. So when you sketch the graph of this function, top function here, it is a linear function, but we will have an open circle at x equals to 0, at x equals to -3. So the graph will look like, well, 1, 2, 3, 1, 2, 3, and then 1.2 is here, -3 is here, but you need to have an open circle at -3. That's the linear. Okay, that's the graph. Well, this point is 0, 6/5. That point is -3, 0. Well, xy intercept. But at -3 will be an open circle. Reason is the implied domain. Okay, the implied domain shows us R except -3. -3 cannot be involved in the question. So open circle there. Okay, next question. Can I sub x equals to 2? No, not yet. So what we need to do is equals to lim x approaches to 2, and then we have x minus 2 factorize the top and x minus 3. And divide by x minus 2. So this equals to lim x approaching to 2 and x minus 3. And then I can substitute now, which is -1. Okay, -1. To sketch this graph, okay, to sketch this one, we will have 0, -3, 3, 0. Okay, like this, and at 2 is an open circle. Okay, this is an open circle at 2, -1. So that's the graph how the graph looks like. Okay, that's how the graph looks like for the top function. It is still linear x equals to 3, x minus 3, but the domain shows us the domain can't take 2, x can't take 2. So 2 will be an open circle. Okay, for f, I can't sub x equals to 0 because denominator will become 0. Same reason. Okay, they all come from the same reason why I can't. So to either factorize or expand. I think factorize is easy because 9 can be treated as 3 to the power of 2. So I have 3 plus 2x plus 3, 3 plus 2x minus 3, and then divide by 2x. And that equals to lim x approaching to 0. Well, remember the lim x approaching to some value. When you haven't substitute the value in yet, you need to keep the lim. Okay, you need to keep the lim until the step you substitute values in to find the y value. Otherwise, you can't really get rid of that. We can see this and this can be cancelled. Okay, the 2x and the 2x here can be cancelled. So what we left is 2x plus 6. Now I can sub 0 in. That's just a 6. That's just a 6. Okay, well, sketch that one. That would be the graph, but there's an open circle here at 0, 6. So that point is negative 3, 0. That's a closed circle, but here is an open circle. Okay, that's the function y equals to 2x. 2x plus 6. Alright, that's how we can evaluate limit. That's the end of the limit exercise. Well, I haven't done yet. Have one more page to go. Continuity. Okay, continuity. So whether a point is continuous at a particular point or not. So that's the third definition. Very, 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 very important. If you can, okay, that. Very important thing. That's the 3 rule you need to use to talk about the continuity. If I'm asking you whether a point is continuous or not, whether a point at that point is continuous or not, what you need to do is talk about those 3 things. Okay, what are those 3 things? Very easy actually. The first one is say whether it's defined at that point. Well, if it's defined, say it. Okay, at x equals to a, it is defined. And fa equals to what? Okay, say it out. That's the define. Second one is test whether limit exists or not. Well, to discuss whether limit exists or not, you need to use the 4 lines there. Remember the 4 thing we just talked about? The left hand side, the right hand side limit. Well, whether left equals to right hand side or not, and then you make the conclusion. Remember that? Limit left, limit right, left equals to right or left not equals to the right, and then limit exists or not exist. The last one is if the first one exists, if the second one exists, and then they are the same value, then it is continuous. Well, to make number 3 exist, you need to have first exist and second exist. If it's not defined, well, we don't need to discuss it anymore. The end of it. Well, that's the end. If it's not limit exists, well, the end of it is not continuous for sure. It needs to be defined and continuous, defined and limit exists, and then we can consider whether it's continuous or not. Okay, that's one defined, second limit, and then we talk about whether they are the same point or not. Let's have a look for the first one. Okay, let's have a look for the first one. Let's write about why it exists or not exists. Right. This is by the definition. Okay, this is by the definition. There's an easier way we can do it. If it's just a multiple choice, you don't need to reason it. What you need to think about is, if you want to see at that point is continuous or not, you only need to think, is the graph connected or not? Is that the graph hold together? Is that the graph just connected? Well, they can be connected this way. They can be connected in the smooth way. They can connect it in this shape. They can connect in any shape. But the thing is, they are connected together at that point. What means not connected? Well, there's a jump. It's not hold together. They're not hand to hand. Okay, they're not together. If there's an open circle like this, it's not connected. It's stopped in between. Like at that point, it's not connected. So it's not continuous. It's not continuous, right? So what we need to, we can look at the graph and then we can say whether it's continuous or not directly without any calculation. Okay, without any calculation. But because we need to discuss and then say why it is exists, then we need to go through those 3 steps. Okay, then we need to go through those 3 steps. Okay, let's see the first one. First one definitely does not continuous, right? That's not continuous because it's not connected together. Why is not continuous? Because f at x equals to 0, it is not defined. At x equals to 0 is not defined. You can see it's not defined. We failed the first one. Well, that's the end. Not continuous. So, not continuous at x equals to 0. Okay, not continuous at x equals to 0. Well, second, do you think it's continuous at x equals to 0? Yes or no? No. At x equals to 0 is a jump, like they are not hand to hand. It's not continuous. So you know it's not continuous. Which one do you think it fails? Is it defined? Is it defined? Is the limit exist? Okay, limit does not exist. So we need to discuss about the limit, why it's not exist. So we'll say lim x approaching to 0 from the left of fx, that gives you a level 0. And the lim x approaching to 0 from the right hand side of fx, that equals to 1. So lim x approaching to 0 from the negative of fx is not equals to the lim of x approaching to 0 from the right hand side of fx. So lim x approaching to 0 of fx does not exist. So at x equals to 0 is not continuous. It's not. Where's my not? Is not continuous. Okay, for the third one, can you see the graph? If your graph is not clear on the notes, just look at this one. There's an open circle there, an open circle there, and then there's a closed circle jump to the top here. Do you think it's continuous? No. Which one do you think it fails? Last one. Does a limit exist in this question? Yes. Yes. Wake up. Let's go from the first one. Do you think it's defined? Yes. Everyone agree that, right? Yes. Okay, define. F0 equals to what? 3. 3. 1, 1, 2, 3. 3. Is the top part there. Okay, number 2. Limits x approaching to 0 from the left of fx equals to. Well, think about, there's a person here. Walk along the path. Go to the 0 location, which is here. Approaching to 1, right? lim x approaching to 0 from the right hand side. Someone here sliding down towards that location. Same point here. So lim x approaching to 0 from the left hand side. That's equals to the lim x approaching to 0 positive. That. So limit x approaching to 0 of fx does exist. That equals to 1. So limit exists. It is defined. What's wrong? What's wrong? They're not equals to each other. So f0 is not equals to lim x approaching to 0 of fx. So at x equals to 0 is not continuous. Okay, so it's not continuous. Make sense? This is a really extreme case. Well, no graph really looks like this. It's too ugly. But like if it exists. This question just shows you, well, because when I'm doing this topic, I was thinking, well, if it's defined and if its limit exists, how it can be a different value? But I can't really imagine a case why it could be a different value. But that's a really extreme case to show you it can be different if there's just 1 point on top. We get 1 point different. So the limit that exists and it is defined is just not continuous because they're not the same. Okay, well, I'm not sure if I will put this question in this year or not. I'm writing the first set, but like you better be aware of that, okay? Well, it's really good. No, I'm not writing the probability set. I will really kill you, like if I do the probability one. No, he's not writing probability. Okay. Well, we are working together on the first one, so.
Wow.
Great. All right. Example 3. 2 more examples. I'm so tired. Let's finish. 2 more examples. Talk about the continuity of the function. Well, we will only talk about the continuity for a function when it's a hybrid function. There's really no point to talk about the continuity for a continuous graph. For example, quadratic. Give you a quadratic, tell me whether it's continuous or not. Well, so silly. Because it's a smooth graph and it's continuous forever. Like, no point. So only hybrid function we was asked to talk about the continuity. And the only thing may have a problem exist is the connection point. Right? Whether it's connected or not. Okay, connected or not. So this graph, domain x is belongs to 0 to 6. And 2 is the connection point. Okay, that's the point 2 in middle. So when it changes from one graph to another. So what I need to do is to test when x equals to 2 on both graphs. Do we have the same y value? If we have the same y value, which means it's an open circle over a closed circle, that's just a connection point. If it's 2 different values at that particular point, there will be one closed circle here, one open circle here, and it's a jump. It's not connected, it's not continuous. So what we need to test is when x equals to 2. 2 minus x equals to 0. And 4 minus x squared equals to 0 as well. So for the first one, it's a closed circle at the point 2, 0. For the second one, it's open circle, but it's still at 2, 0. So it's the same point. Okay, it's the same point. It's connected. So it is continuous. Is continuous everywhere within the domain. Okay, so everywhere is continuous. If the connection point is connected, then we have a smooth graph on the left, smooth graph on the right, must be continuous as well. So within the domain, it is always continuous. Okay, so that's how we test about the continuity. Okay, for the second one, well, the domain is x belongs to -3 to 3. 6, not 3. And then there's a point 3 we need to talk about because 3 is the connection point. So we will say when x equals to 3. You can't do F3, okay? You can't do F3. F3 only means you can sub 3 in the top function, not the bottom. Don't do, because I have seen students do F3 equals to like this. It's not going to be this. You can only substitute 3 in one place. Remember the test you did on the first pretest? You can only substitute one x value into one function for hybrid, not both. Okay, not both. Well, if you sub 3 6 here and you sub 3 that's a 0 here, that's a wrong notation. Your F3 not going to give you 2 value. It can only give you one value, which is the 6, not the 0. Alright? Well, someone looks so confused. Anyone confused? Why I can't do that? Understand why we can't do that? Because hybrid function we can only substitute into one. F3 means F3 in the proper place. 3 is in that function, not in the other one. That's an open circle. You never can get 2 values for a function. One x mapping to one y value, not going to give you 2 y values. So F3 is not a good notation to use. We can only say when x equals to 3. 2x equals to 3. Not fx is 2x equals to 3. And then x squared minus 9 equals to 0. That's the way we can say it. We can talk about it. We can't mention F3. F3 is just 6, no discussion, okay? No doubt. But like we can see, there's a closed circle for this one. At 3,6, that's a 6, not 3. 3,6. And here is an open circle at 3,0. You can see that's a jump. Okay, 3 zeros here, 3 threes here. There's no connecting. They're not connecting. So the conclusion is not continuous at x equals to 3. But it's alright for anywhere else. Other place is fine, just not that point. That point is not connecting. So it's not continuous at x equals to 3. Any other questions? Yes? But if they ask you to show, you show it. I think most of the question will be multiple choice. The multiple choice question will ask you whether it's defined or limit exists or like differentiable. It will be multiple choice. It's not going to give you a short answer question to ask you to talk about that. Well, except in the set. Or if it's in the set, it can ask you very specific, draw the graph or reason it or something else. Well, last year I think the set is in this like this. Give you a hybrid function and then you draw the graph and then talk about why it is not continuous at x equals to 3. So you need to say left hand side limit equals to 0 and right hand side limit equals to 3. Left hand side limit is not the same as right hand side limit, so that's why limit does not exist and that's why it's not continuous. Yeah. Any other questions? Well, easiest way is to show by graph, but it's too much to do, so I'm getting lazy, don't want to draw it. You can show it by yourself. I believe you can do a quadratic plus a linear hybrid. If you can't, don't sleep tonight, learn for hybrid functions. Alright, any other questions? Done.